Hi, this is a video that's been a long time in the offing. Unfortunately, I haven't got round to producing this, and in some ways I was hoping somebody else would, with better equipment and a better presenting style, to be honest with you. So what I'm going to do is try and explain to you about the reason why, if you have, say for instance, an LED like this, it remains lit even though it's switched off. So I've emulated that using this piece of circuitry. Now, I did have a video beforehand which showed you when the circuit was wired as a switch neutral, you had this sort of fault, and if you change the wiring to switch live, which is the correct way of having it, that it stopped happening. But what I've noticed that a lot of people have talked about why this actually lights, but they haven't actually talked about the asymmetry. Just changing the wiring, what would appear to be just reversing it, makes this stop. So hopefully in this video I'll explain that. I also want to go through 5 different reasons to stop this happening, and I'm going to do some diagrams and stuff, and so there's a lot of content in here, and I don't think I'll be able to cover this sufficiently in one video. Now, I'm not a qualified electrician, but I am conversant with electricity and electronics, so I do understand the principles behind electricity, but I haven't taken any exams for the regulations for wiring. Be aware, this is not recommendation, this is just purely why these things are happening, and it's just for information purposes only. It is not intended for implementing these particular changes, but to give you a flavour. If you do want to implement the changes, then I suggest that you go through and talk to a proper qualified electrician or somebody who is competent, and they need to be competent to a certain level, not just aware of electronics, because there are certain things that if you get wrong could be quite disastrous. Now, talking about things that could be disastrous, this is actually live mains at the moment, so this is actually lethal. Do not even try and replicate this because it is extremely dangerous. I have no option, I need to use the live mains. So as far as my test kit is concerned, this is the bulb which is susceptible, and I'll explain why that's the case. I've got here a multimeter, and this is just across this pendant. I've got the mains coming in. I shall just pop this out so you can see what I'm using. I'm using a home plug to do the main switch, and I'm also using an RCD, but it's an active RCD, not a passive. I want something that's active, which means that when the power is disconnected, it will open the circuit, and this will not re-energize until the reset is actually pressed in and latched. So that just gives me an element of protection. That's my setup. Why is it so simple, considering that what I'm doing? Well, that's what I have, so that's what I'm going to use. I've got a selection of bulbs here. These aren't going to be that relevant, but I just want to quickly show that, say for instance, let's just quickly test, make sure this is off, which it is. And I know people deride these, but in this particular scenario, it's good enough. As I said, that's the cap, which is just basically allowing you to see the thing when it's demonstrating, so just for the initial intro, so you can actually see what it looks like and note if that's similar to what you're getting. So let me show it fully switched on. So this is what the lights look like when they're fully on. I'll take this out. So this is a susceptible bulb. It's not flashing as it did in the previous video because of the ambient light is stopping it from causing the camera to flash. You'll notice that this pendant has got retractable conductors for safety. So I've got here, this is a non-susceptible LED bulb. Again, you'll see it's just as bright. I've also got a halogen, which is 60 watt halogen. You see it's pretty much like the 8 watt LEDs. I won't keep that on for long because it will start melting the board. And I have here, which is the CFLs, and I'll put that in and you'll see it's slow and it will slowly get brighter. But I just wanted these as a selection so you can actually see the difference between them. So with the LEDs, the strike voltage is very, very low. Again, I'll explain that a little further. So you can see 240 volts right here, or 246 in this particular case in this house. What other people have done is that they have explained correctly that if we were to look at, say for instance, the standard junction box which you have in the UK, 4-terminal junction box, and I will draw the incorrect wiring of switch neutral, which is generally what you see causing this fault. You have a loop in and loop out, and that's just basically your power cord, and that would go to different lights along the way. But this is what we call the ceiling rose, which is holding the pendant or this could be an actual 4-terminal junction box which is hidden within the floor or the ceiling void. So in this particular case we've got two connected, and for it to be incorrect as switched neutral, the live would go directly to one side of the bulb, the other side coming from the bulb would go back to the terminal, and that would then go here, and it could be quite a long piece of wire. So I'm just going to do that sort of concertina thing to show that it's actually can be quite a long line. This particular piece of line from the bulb to the switch is a floating line. So when this is open, as it is now, this will float up to the same voltage because there's no current flow. Of course, when there is a sort of glow, there is a small current flow, so this is actually just floating. So it floats around the 4 mains voltage. So what happens to the other side? Well, that comes from the terminal and goes to the switch, like so. So pay no attention to these bits at the bottom, they'll become apparent fairly shortly. I'll put that concertina in to show that this could be quite a long line. This tends not to be a long line, but if it is very long, it can actually count in your favour. Again, I'll try to explain that in a mo. So what people do is they say that the reason why this is conducting is because there's a stray capacitance here. Say with this long line, the switch and the cable, the length of cable, is causing a capacitance here, and that's allowing enough electricity to go through this and conduct. I will emulate that on this by first of all making sure it's switched off. Say for instance pulling this out and putting my cap in, and this is I think this is a 2 nanofarad cap which I'm using at the moment. So it's 2 nanofarads. It's saying 2144 picofarads, which is essentially I think it's actually 2.2 nanofarads. So I'll put that in and I'll fire this up and I'll put in the susceptible bulb, and you can see it's lit. You might want to, when I put those things in, look at the voltages of this thing, because you'll notice how it's drawn right the way down when, say for instance this, which is about 70 ohms, but these things, that's about 80-90 volts, and this is a septal one, and you'll see it's 189 volts, floated up to 230 now, and putting that in, you'll see it draws it down. So clearly these things, these ones that are not susceptible, are doing something, whilst this one isn't doing a great deal, and the voltage is high enough to strike the diodes. And the diodes, basically, if they're not below the strike voltage, this is just seen as an open circuit, and so it doesn't bleed down, whilst these have got a shunt. But I'll explain a little bit further in, because there's 5 ways to fix this. So the first way is to get the right product. And personally I think the susceptible ones should be banned. There's no reason for them to actually produce these. It's saving fractions of a penny to not put the cap or resistor in these things that act as a shunt. I showed you the switched neutral, and if we look at the switched live, well, there isn't a great deal of difference. Obviously the wires are swapped, and we can put the stray capacitance here, which is represented by that long line, and this switch, and let's emulate that on this thing. What do we want? We want to put this so in this particular case, this inner circuit here is the neutral path and this is the live path. So I put this capacitor into that location, and let's see what happens now. So I'll switch this on and we'll put the susceptible bulb in. And so, as I said before, if you wire it as the switch live, it doesn't seem to light up, but clearly it is lit up at the moment, so we're missing something. There's an element of this that's just not there. What is it that's missing? The element that's missing is the earth, or ground, and so we'll draw that in. So I'll draw this here. That's the ground cable, and we use Twinkor and Earth. I think many people, many countries will be using the same thing. As far as the pendant is concerned, a lot of pendants in the UK don't actually have an earth, but if they are metallized they must have an earth. But the earth in this is so short it doesn't really come into effect. Where you have a long line, the earth is part of the effect, and it usually goes to a terminal, which is usually in the switch patris, but not actually on the switch body itself. We now have this earth in there. One of the things that I was going to draw here, which I better draw now, is that we have switch live and switch neutral. So if I draw that. With switched live, I would have had the equivalent of my long line there, and I would have had my bulb here, like so, and of course the current went round and lit the bulb. Switch neutral is the caps here and the bulbs there. As you can see, the only difference between the two is the caps on the other side, and as I said, there has to be something different. So now I've drawn this earth in here. How's it actually changed the switch neutral? Well, the elements that I have here, I've got a capacitance to this between the cap and this floating live here. I've also got that to the neutral, which I have originally drawn in, and I also got a certain amount of it which is actually going to the outside world, which I'll draw as a capacitance to the outside environment. So all of these things add up, and effectively what it's like is having a capacitor in addition to that capacitor. So I've increased the capacitance. In the case of the switched live, if I did the same thing again here and I drew my earth in like that, my loop in, loop out, and then I put my earth in here, and of course this is a long line, so I should draw a little concertina in there, and that goes to a terminal which you can use. So the important thing is that you have additional capacitances here, and with this what happens is for this to light, this will be lifting up in voltage as it draws across some of the voltage there, and as soon as it lifts up, well, there's going to be an environmental effect here with the capacitance again, like so, and also there will be a little bit of capacitance to the ground, and also the live wire, which is fixed live. Well, in fact, to be honest with you, that probably is quite irrelevant because it can supply as much power as it likes, so it can supply as many electrons as it needs to. So I think having a capacitance connection to ground is going to be fairly irrelevant for this because it's not going to affect the capacitance. But what's the net effect? If we look at this diagram here, it's going to appear as a cap from here across the bulb. I'm summing up the capacitor and I'm making it worse here, whilst here it's actually acting as a voltage divider, and as I said, when it doesn't hit the target voltage, the clamping voltage, then this is just as though it's just two caps in series. The second thing is, if you have bad wiring and you have a switch neutral, you should have it rewired to switch live. In the UK, it wasn't actually an issue before because we used to use bayonet connectors for the lights, and in actual fact you didn't necessarily have to even have an earth in your lighting circuit. But as things progressed, the earth was introduced, and you'll see here that the two conductors are separate from the jacket. But since we went to Edison screw and things changed, the jacket here is actually a conductor. It is important it's polarised correctly so you don't get shocked or electrocuted when changing the bulb, and it's certainly more serious in countries at 240 volt to have that than in the States with 110. But more accidents are caused by people jumping, being surprised and doing something than actually being physically electrocuted. Obviously your heart can stop with electrocution, but you're more likely to actually do something else which causes injury to you. So let's emulate that. I'm going to do this one first, which is adding the cap. Let's just make sure this is off. For the neutral, I'm going to emulate that by putting my cap in as I had before. And the earth element, I don't have an earth on this, but the reason the neutral is called neutral is because it's connected to earth at some point. And so I'm going to take a little green wire here and pretend that that's the earth. Unfortunately I melted the board and that's why I can't put an earth on this, but it doesn't really matter because you can understand what's going on here, or at least I hope you can. This isn't so rushed that it's all confused. So if I put this in here, this is the equivalent of my caps being summed together like so. Let's switch this on. And you see the susceptible bulb has come on. It's slightly brighter than it was before. We should look at the voltage, because you can actually measure the voltage and it does give you a good idea of what's going on. So if it's high, like that, it's almost at full mains voltage. Okay, it's moderated, it's ballasted by the caps, but still, it's a good indication that you're probably going to have a problem. As I said, get the correct bulb, that's the route that you should be taking is not to buy things like this, which are not such good quality. Sadly, they're the same price, and generally you don't even know until you buy it to find out. But if you look into it, I don't know if it's so clear, you can see there's pretty much no circuitry in there. And if you look into the base of this, you can see that there's a little circuit board at the bottom. Very difficult to see because they look practically identical in every other respect. Here we go. We can see that when this is put in, it's doing that. If I put this in, nothing, because that's good. It syncs the voltage, as you can see here. And similar, CFL is the same sort of thing. They do flash for bad ones, and I'm not even going to bother with the halogen because it's just not going to do anything. Next one is to test. We are going to emulate the switched live. Again, we've got the environmental effects, which I'm going to emulate with these bits of green wire. So as before, we have our cap, which is here, and that's going to cause the thing to light up. So we can see it's lit, and then we're going to take this and we're going to put this across to show the additional capacitance, the environmental effects. And if we switch this on, you can see that there's pretty much nothing. Let's put a slightly larger cap in there. The bulb still isn't lit. You'll notice that if I take this out and you look at the voltage here, you'll see it's 120. So it's actually split the voltage here. And as you can see, the environmental effect of having that cap, and that is the next of the 5 solutions, number 3, which is you can shunt across that bulb. So the easiest way to do that is, if say for instance you have GU4s, the tiny little LEDs, is to put one of the tiny little GU4 halogens with the rest of them, and that one little halogen will be across this and it will consume that power. So this is on at the moment, I think. I'm going to do something extremely dangerous, so I'm just going to carefully pull that out, and you can see that it's lit up. So it's entirely down to that cap, which is shunting. The next thing is to look at final 2 solutions, which is to either use a resistor or use a capacitor to actually do this shunting. Say for instance we have this situation where we've got our environmental effects. I mean, you can get this on a very long switch live, or if there is no earth wire in the circuit. So let's put these in and we'll switch this on, make sure that we intend. We have the bulb going, and what I'm going to do is, rather than adding this, which is about 70 ohms, they're much lower resistance when they go off, so the resistance will collapse down to about 70 ohms. As it heats up, the resistance goes up. You call that positive temperature coefficient. When it's really cold, like this, at room temperature, then it's actually quite a low resistance. But I can do a similar sort of thing, but I have to be careful with what resistor I use, and I have to choose the value carefully. I'm not really going to go too much deeply into this because it's going to use up too much time, but I've got here an 820k resistor, and you can see that 820k. It's looking at 862k, which is within tolerance. You have to be very careful about this. This is a 1/4 watt resistor, and if you were to put it in your circuit, you have to be careful where you put it because you have to think of end of life effects. So for a resistor like this, not only is it quite small, but it has to be a fusible resistor. It has to be the right sort of size. So in the region of about 800k to 1 meg is probably sufficient, because then I only dissipate roughly about 0.1 of a watt, and that's about half the value that this can take. So you never want to run it at full power, and you've got to consider peak voltage, because power is the rate of energy, and if you use RMS, like for instance 240 RMS, you have to consider that that's the average. The peak is more like 340 volts, so you take 340 volts and you use that to work out the power of this. So 820, and I won't go through the maths, I did do that before, it just consumed up too much time. So as I showed, this lights up, and I'm going to put this resistor across here, and I'll show you in the diagram where I've put it. For the bad circuit, switched live, I put my resistor here, so that's my resistor, which is 820 kilo ohms. Across that that light, and that's going to sync the power. So let's switch this on again. You see there was a flash on this, but it's not lit anymore. And again, if I take this out, you'll see that the voltage has dropped, in this particular case 158 volts, but it's not lit. Now, this is the part where it seems like a lot of people are blindsided. Manufacturers do put the shunt, they use a shunt capacitor as opposed to a shunt resistor. You have to shroud this, and where you put it is quite important. So, for instance, a lot of people tend to put these shunts in this location, and this is the junction box with your main wiring. This is a bad location to use because you have to think of worst case scenario. So if this thing lights up because you haven't used a wire wound or metal film fusible resistor and it burns your wiring, you might have to then rewire your internal electrics, and that could be extremely costly. So the place to put this, if you were to have one of these, is within the light fitting away from your wiring. And in this particular case, the location of choice for me would be in the pendant at the back here, where you've got access to terminals for the pendant itself. Let's put this back on. These are 1 nanofarad caps we've got here, so it's lighting up. The last solution, and the one that I kind of prefer, and it seems to be quite rare, nobody seems to really talk about this, but it really is the way I would do it, and this should be inside the bulb, and that's to use a cap as a shunt. So I've got the 2 nanofarad cap here, and I'm going to put my cap in this location. So the cap, when you're working these things out, the voltage across the large cap will be smaller and the smaller cap would be larger. So putting a larger cap than the combined amount of these will mean that the voltage will drop across the bulb, and of course it will never get to the strike voltage to cause it to glow. So let's do that. And this is a 2 nanofarad cap. Put that across. There we go. So again, if you look at the voltage, it's gone up to 140 volts. We'll take this out. Still there. As you can see, it's not lit. Again, with the caps, these aren't just any old caps, these are mains class caps. The mains, although it is notionally 240 volts, you can't trust it. It's very dirty electricity. It has lots of surges, it has spikes and the like. Anything that's put into the mains has to pass a certain standard. So here I've got a little power supply, and you can see actually where I got my little X-rated 2 nano and 1 nanofarads. And you can have this. This is, I think this is 470 nanofarads. And again, this is what they call an X2 class, whilst these ones are slightly better, and they're X1, Y1. So usually you have X or Y, but this does both, which means it's just passed both of the standards that it's tested to. And what they do is they put surges onto this. It could be 4,000 volts, 1,000, 2,000, depending on what the parameters are. But the important thing with these is the end of life effects. They do not catch fire, because eventually a lot of caps tend to go short and they use a lot of power at that point and catch fire, but these don't. These are designed not to, so it's important that you use the right sort of cap and also the right sort of value. So in this particular case I've got 2 nanofarad, which you can see that it's not lit, it's shunted out, and this is the worst case scenario. So I've got quite a lot of capacitance on here, so I've got 2 1 nanofarads, and you just add them together when they're in parallel. So that's 2 nanofarads split with my 2 nanofarads. If you had slightly less, and Internet Wisdom says that it's about 100 pico per meter for the wire. This is extremely dangerous what I'm about to do. I'm again going to just pull this out, but I can get away with doing this. You'll see this lights up. If I take that out so that it's 1, and that's going to be in series with my 2, you'll see it's dropped the voltage even further. So it's 73 volts, you can see on this. And you know, it's not getting anywhere near, because this is essentially like an open circuit, because it's not getting to the strike voltage of the diodes. So you'll see absolutely nothing at all on this. With these, which have the thing built in, you'll see it drop even further. So anyway, I hope that explains. This is a long video, and I think again I might have got away with it with a bit of editing to knock off a few minutes and it would be acceptable. Essentially, where this would go, it would go in the same place as a resistor, but it must be a mains class capacitor. Do not fit these things, the resistor or the cap, if you don't know or unsure what you're doing. It's not good enough to just put something in that will do at the time or is 240 volt rated, such as things like these. Although these are rated at 240 volts, they'll take the power. The end of life effects are unknown, and this could trash and cause a lot of expense to you. Thank you for watching.